Thank you. Good evening. Right, just a very, very quick background on just to say what a body engineer is. So basically, we're responsible for the bit that was spinning around. That is the body. Sometimes people call it the chassis or the monocoque, but that's the bit we do. I've only had one proper job in body engineering at Jaguar all my career. Should be pretty good at it by now, and if I'm not, then shame on me. But my job really today is to explain to you, and it's a little bit of I was intrigued at some of the earlier presentations, and it's a little bit of quite a difference to what you've been listening to the rest of the time at this conference. But really, I think some of the challenges are the same, and some of the things that we have to address in the long term. I was dying to sort of join in the panel debate, but I thought I'll let the more learned amongst you to take part. But we have some serious challenges in the automotive industry, and there are perception and there is reality. And we're going to try and explain some of the reality and hopefully overcome some of the perceptions about Jaguar and Land Rover tonight.
We were conceived on a beach in 1947 and born with a sense of purpose. We grew up strong, self-assured, and prepared to face a challenge. Never afraid to get our hands dirty or get a bloody nose. Ready to pull our weight, and everyone else's, at home and abroad. Then, looking to the future, we raised a family to be proud of. Offspring with the same intrepid DNA, the same steely determination. Like father, like sons. Not driven by vanity or fashion, but a desire to serve. There to face the new millennium with confidence and capability. So 65 years on, we continue to go above and beyond.
So hopefully perception and reality number one. First of all, perception, Chelsea Tractors, reality. 85% of the Land Rovers and Range Rovers that have ever been made are still on the road, most of them actually off the road. We are the supplier of vehicles to the Red Cross, and it is a charity of choice that we support. And most of our Range Rovers and Land Rovers are not used in cities or to take kids to school. They are used as purposeful vehicles. Ask anyone that owns a vineyard or a farm or any other what their vehicle of choice is. So let's just talk about some of the trends affecting the global automotive industry, because they impact on what we do. First of all, everyone knows about things are just getting more expensive. They're also more volatile, and things like oil, materials such as aluminium, precious metals, etc. All the things that we generally need to build our cars that are generally increasing in price. We've also got the other extreme where CO2 and fuel prices are increasing, and there are CO2 restrictions globally now. It's not just a European or a London congestion charge thing. There are CO2 legislation either on the books or being passed through most parliaments in most countries all over the world. As automakers, we've seen the trend towards downsizing and hybridisation and electrification of powertrains. We are on that journey just as every other manufacturer is. We no longer make a V12 engine. We don't believe it's environmentally responsible to make a V12 engine. We're using what we call power boosting and electrification to augment the base engine in most of our cars. I took my wife to Holland a couple of weeks ago in the new F-Type, the two-seat roadster that we're just about to bring out. Pulled up to a set of traffic lights, engine went quiet. wife started looking at me a little bit worried, thinking, oh damn, he's taken a prototype and we're broken down at the first set of lights. Put my foot down, off we went again, engine starts, go. And she kind of said, well, what is the point of putting stop-start technology on a sports car? Well, it saves between 5 and 10% fuel economy in the real world. So that's the point. You know, it's a relatively simple piece of technology in terms of electrification of the powertrain. We've also seen a movement away from big SUVs, body-on-frame cars, as we call it, where there's a separate ladder chassis and a body sitting on top of it, to more integrated, smaller vehicles, more car-like SUVs. So let's be absolutely clear. We make SUVs. We're happy to make SUVs. People love SUVs. They love people carriers. They love SUVs. They love big cars. If people didn't want to buy them, we'd all be driving around in Fiat 500s. So our goal is really to try and take the things that people want to buy and make them more environmentally responsible, and really think about what the total carbon effect is. We've also looked at downsizing, so making smaller premium vehicles. So the Evoque is a classic example of that. The Evoque does pretty much everything a full-size Range Rover does, but in a much smaller package, with a CO2 output similar to something like a Mondeo or a Focus. You know, so 129 grams is the CO2 on an Evoque, and really something that perhaps, unless you travel, you don't really see a lot of. But the European and the US market is pretty much mature for the car industry, as it is for a lot of other commodities. But all the growth is in the developing world, in China, in India, Brazil, Russia. We went on holiday this year, last year, sorry, to Indochina, to Vietnam and Cambodia and Laos, and I was absolutely amazed at the number of Range Rovers and Range Rover Sports that I saw during my visit. I didn't expect to see any, to be honest. So there's basically, I think there's one Honda motorcycle for every second person in Vietnam. So there's about 100 million people live there. There's over 50 million Honda 50cc Hero motorcycles. But they leap straight from a Honda motorcycle to an SUV as their car of choice. And if you've got any money at all, you just go out and buy a Q7, a Porsche Cayenne, a Range Rover, or a Range Rover Sport. So there's a real dichotomy in those markets. But those vehicles are very, very practical. So where there isn't the infrastructure that we would have in place in terms of the motorway networks, etc., in Vietnam and places like that, they can cruise happily down the motorway in their SUV, get to the middle of nowhere and carry on their journey and go to wherever they want to go to. So that's why SUVs is the biggest growing market segment in the auto industry. Something like 20% growth versus other things such as the E-cars or the D-cars. That would be something like the Mercedes E-Class or something like that, where actually that market is completely static. If anything, it's shrinking. So people are moving out of luxury S-Class Mercedes and even XJs and moving into luxury SUVs. So that's kind of where the motor industry is going. But we have got this challenge. Every single manufacturer has this challenge of CO2. We have already got legislation in Europe and in most of the developed countries, and we're now pretty much agreed. If you went back to the turn of the century, when we were all arguing about does CO2 and climate pollution really exist yet? Well, yes, it does, but we were arguing about what should be the limits for cars. And it was varied by over 100 grams per kilometre between the US as the sort of most optimistic, if you like, in terms of what does a car need to do, to the Japanese, who were the most pessimistic in terms of the targets set. But when you look out to 2020 and 2030, actually the legislation that we're putting in place is pretty much the same. So there's only a 20 grams per kilometre gap between the US prediction of where we need to be and the Japanese prediction of where we need to be. And the European glide path is pretty much smack in the middle of that. So in Europe, we have and have had for at least 5 years what we call a European Transport CO2 Plan. So let's just have a quick look at that. This is a bit of an eyesight test, so I'm not actually going to go through it in a lot of detail. Let me just highlight a couple of things to you. So along the top, you've basically got the CO2 targets for the European fleet. So that's every car, take an average, and that's where we think we need to be. So currently today, we're around about 140 grams. By 2020, we think we need to be around about 100 grams, probably sub 100 grams. And by 2030, we probably need to be sub 80 grams. Now, to put it into context, if you just measure total energy and CO2 released, it's about 40 grams per kilometre if you cycle on a bike. So a car at 80 grams is going to be, twice the CO2 of you cycling to work rather than going in your car. And depending on how you calculate it, at 80 grams, we're probably as CO2 friendly as getting on the train. And probably even slightly better depending on your occupancy use, both in the car and the train. So that's where we really need to get to. But to get there, we have to do something fairly significant. Every single car in every single segment has to lose a significant amount of weight, and that's somewhere between something like a small Fiat 500, around about 100 kilograms between now and 2020. And the same thing again between 2020 and 2030. And for a large SUV, that's more like 250 to 350 kilograms, depending on the market segment and the powertrain that vehicle's got. So a fairly significant challenge. Taking 350 kilograms out of anything, let alone a car, is a fairly big task. So let's just have a look to see how we can do that and what the benefits to the CO2 are. So this is just a bunch of European cars plotted on a graph. The blue little dots are petrol cars, the red triangles diesel cars, and the green are hybrid cars. And you can see that if I make a car that is 2,000 kilograms, it emits about 250 to 300 grams of CO2 per kilometre. If I make that same car only 1,500 kilograms instead of 2,000 kilograms, I immediately get the CO2 below 200 grams per kilometre. So I'm now in a situation where my petrol car is more efficient than my diesel car, and my diesel car is more efficient than a hybrid car at 2,000 kilograms. So really, the weight is a significant factor towards the CO2. In fact, next to the powertrain downsizing, it is the second most efficient thing to do to a vehicle, so make it lighter. Now that's where we think we need to be. We need to be in that 1,500 kilogram weight category by the time we get to 2020. But really, by the time we get to 2030, and this is where the real engineering challenge begins, we have to be down at 1,000 kilograms. Now, to put that into context, a smart car weighs 820 kilos. So that's imagine making a full-size Range Rover the same weight as, or a little bit heavier than a smart car. That's a fairly significant challenge. But also to put it into context, the Mark I Golf was only 780 kilos. The Lotus Elise that I drive when I'm not working, and my fun car at home, weighs about 800 kilos. So we can do it. The car industry can make lightweight cars. It's how do we make lightweight cars that people want to buy, that have the right equipment and the right safety and all the other things that we've got used to over the last 30 or 40 years. So we have to save significant weight, but we also have to look at things like aerodynamics and powertrain downsizing at the same time. So this is JLR's roadmap for the future. We have a three-pronged attack. Weight is the bit that I'm going to do, so I'm going to reduce the weight of the body first of all, because that is the big heavy bit to start with, but I'm also going to reduce the weight of the chassis, all the closures, and move on to every single part in the car to get significant weight out. And I'll show you the model for that when we talk about the Range Rover in more detail. We also have to do what I said earlier about the propulsion system. We have to take petrol engines and diesel engines, downsize them, power boost them, add electrification to them to fill in the holes that you normally associate with turbochargers. So anyone that's my age or older that remembers Saab turbos with huge amounts of turbo lag, what we do is we add an electric motor in, and that fills in the lag between the turbo spinning up and you putting your foot down. So there's all sorts of clever tricks going to come along in terms of propulsion, and most people in the next 5 or 6 years will drive a car with some sort of electrification in it, albeit it may not be visible to you as a customer. Parasitics is the next big area that we think we need to work on. Cars have got more and more aerodynamic over the last 10 years. We realised that fuel economy at speeds above 50 miles an hour are significantly affected by your rolling resistance of your tyres, your aerodynamics, and a few other things, the losses in the drivetrain. Most people in this room probably don't check their tyre pressure very often, but just keeping your tyres to the right pressure will give you about 2 to 5% fuel economy improvement depending on the type of car you're driving. So if you do want to save between 2 and 5%, once a week, check your tyre pressures, and that's an easy win. So there's lots of stuff like that. The car at the minute is a very inefficient place to be. It's not like, we're probably in the car industry where the housing industry was probably in the 60s or the 50s. You know, we haven't got double glazing, we haven't got cavity wall insulation, we haven't got loft insulation, and basically the heating systems that we have, the heating and cooling systems that we have in the car are designed to give you perfect comfort, not to save energy. So we're looking at how do we use the waste heat from the exhaust system and use that to heat the cabin? How do we use solar glazing to keep the cabin cool in the summer and comfortable in the winter? So all of those things will start to appear in the car in the next 5 to 10 years. But my bit is the weight, and I'm going to talk now for the rest of the time on weight reduction and what we can do about weight reduction. About 99% of all cars made, and that's probably, well, China made 18 million cars last year, just in case anybody wasn't paying attention. So China is the biggest car producer in the world today. The Americans made about 14 million, just to put that in context. But globally, we probably make in excess of 50 million cars a year. So it's a lot of cars. Europe's about 12 million total. So, and then the emerging markets, South America, Russia, and other markets all add to that. So 99% of those are made from steel, and most of them are spot welded together and made from what they call stamp parts, pressings, made from mild steel and a collection of various high-strength steels that we've developed over the last 10 to 20 years to try and save a bit of weight in the steel body. So we've introduced what we call ultra high strength steels, things like boron steels, martensitic steels, but really all they've done is kept the march of time stable. They haven't really decreased the weight of the average car. They've either been weight neutral or just stopped us putting on more and more weight. If you just look at the cars in the 90s and then look at where we are today, on average, we put on about 10 kilograms a year for every manufacturer. So it doesn't matter which manufacturer it is. Every year, for the last 20 years, 10 kilograms, that's 200 kilograms. Your average car has got heavier over the last 20 years, which is a shocking figure, really. But, I don't know, let's do a quick straw poll, because there's a lot of youngish people in. Who's over 40 in this room? Put your hand up. Right. How many kilos have you put on since 20 to 40? It's not 200, but you've got to remember a starting point of a car. So I'll happily own up to having put on at least 10 kilograms and probably a few more than that in the last 10 years. So the car's the same. You know, as we get older and more mature, we want more out of life. We tend to have more disposable income, and we want more comfort and convenience. We actually go out and buy bigger houses, bigger cars, all the other stuff that is. So all we've done with the development of the high-strength steels is really try and stop the rot a little bit. It's not like going down the gym on a regular basis. It's just really cutting back a little bit on our diet. The real weight saves are in what we call the light metals and the composites. You can see that aluminium, magnesium, carbon fibre all offer significant weight savings versus the products that we make today. Aluminium, probably the closest in terms of the factory to steel. We can get at least a 40% weight save. Magnesium, if we could make a magnesium car, we could get a 50% weight save. We can make carbon fibre cars, but there are several problems with carbon fibres. One is the cost of it. So the aircraft industry has rushed towards making aircrafts out of carbon fibres. Very good reason for that. Aircrafts basically have a very long duty cycle. They know exactly what they're going to do, and it's all about how many passengers can you get on for the payload that you've got. So they're willing to pay a lot more for weight. Anybody know who's willing to pay the most for weight in the whole of the transport industry? Most people say, oh, it's got to be military jets, you know, they'll pay. It's Formula One. Formula One will pay up to $20,000 a kilo weight save. And that's why everything's carbon fibre in Formula One, including all the suspension bits, some of the engine bits now. The car industry, because we can't pass that on to the customer, will only pay between 1 and 5 euros or $1 and $5 per kilo weight saved. So carbon fibre at around about, we've just built a carbon fibre prototype. That the material cost alone in that was £8,000, and the actual cost to manufacture was about £45,000. Put that in the context of a steel body today at £750, and you can see that actually we can't just pass on £45,000 of cost to the customer and say, by the way, would you like this nice lightweight Fiat 500? It's nearly half the weight of the car you're driving today, but it is going to cost you £60,000. Probably not going to sell many of those. So carbon fibre is definitely on the road. There are a couple of issues with carbon fibre other than the price. One of them is the amount of energy you actually use to make the stuff in the first place. It's basically made from oil, or has a large use of oil in its manufacture. The second thing is not very recyclable at the end of it. Because it is a composite, you're putting resin with fibres. It's very difficult at the end of life to separate those resins from the fibres unless you incinerate the resin, which isn't a very environmentally friendly process. So we're working on all those sort of problems. So we're going to concentrate on the light metals because that's what we're doing today. And I'm going to talk specifically about the new Range Rover. So the Chelsea tractor, as some people know it as, we don't know it as the Chelsea tractor internally. In actual fact, most of our customers don't know it's a Chelsea tractor either. So we had Greenpeace come to visit our factory unannounced about 5 years ago, chained themselves to the production line and called us environmental hooligans. And then we showed them the life cycle analysis of a Toyota Prius, a Toyota, the big SUV, Land Cruiser, and the Range Rover. And we showed them just the simple maths and said, by all means, go away and check it yourself. But because of the batteries and the number of rare earth elements in a Prius, actually, its total carbon footprint isn't very good. So please be factual rather than looking at perception before you make judgments. So what was our target? Our target, just skipping back, sorry, was to save 400 kilos. I showed you the slide earlier that said we had to save 350 kilos really by 2020. We actually set an internal target of 400 kilos. We did better than that. We saved 420 kilos overall on the vehicle. At least half of that was from the body, so that's my bit, so I feel quite proud about that. But we set our target of not reducing the attribute performance of the vehicle. So the vehicle had to do everything the previous car did and do it better, and the customer not notice any detriment in NVH, durability, safety performance or anything else. So we used a combination of aluminium and other lightweight materials basically to reduce its overall carbon footprint. And we'll talk more about carbon footprint rather than tailpipe emissions, because we make big heavy, we did make big heavy cars. We'll never make small light cars. What we want to do is make big light cars. And so we want to measure the total carbon produced in the overall footprint of the vehicle from its raw material manufacture through the manufacture of the car during its usage phase and how recyclable it is at the end of it. So just to put the context, the weight of the new Range Rover body in context, it is, and I've called them competitor B. B always stands for BMW in Jaguar Land Rover term. A always stands for Audi. So there's a clue there. And D, D stands for Daimler, but we didn't want to embarrass them by putting them on this list. So competitor B is the 3 Series BMW. So the weight of a Range Rover body shell is 23 kilograms lighter than a 3 Series. And it's 85 kilograms lighter than an Audi Q5. So that just puts it in, that's fact, not perception. So that's what making something of aluminium does. So I want to just talk about how do we achieve that then. So some of the technologies that we go into to making that. We've been making steel cars, steel monocoque spot welded cars for about the last 70 or 80 years. So most of the car industry is pretty good at it. We started our aluminium journey, or our lightweight metals journey, about 1998. I think I first started mucking about with my prototypes. So we're a reasonable way into it, but nowhere near the sort of learning and intelligence that we've got in terms of the steel cars. So what we've done over the last 12, 15 years is developed a whole bunch of new alloys that give us the sort of performance that we want out of steel cars, but with this 40% weight saving. So we've developed new crash alloys, we've developed new formable alloys, so we can make the sort of shapes that we used to make in steel, now in aluminium. One of the problems with, if you like, the conventional or the traditional aluminium alloys is they weren't very formable. They were all right for hanging on the side of buildings, but they weren't very good at doing this sort of thing. So we've made them so that they can concertina nicely. We call this the Viennetta alloy, for obvious reasons. But basically it can absorb a lot of energy in a fairly small space, and that means versus the 5754 alloy that we started off with, actually it absorbs over 30% more energy, and it gives us a 20% weight save, which is equivalent to about 6 kilograms per vehicle, and that relates over the vehicle life for the whole fleet of 12,000 tonnes of CO2 reduced by saving that 6 kilograms per vehicle for that particular crash alloy. And this is what it looks like in the real car. So hopefully the customer will never notice the difference between his steel car and his aluminium car. So we've got a nice Viennetta alloy in the front of the car, and then some other very stiff aluminium alloys around what we would call the passenger safety cell. We've also came up with some new formable alloys, because traditionally, as I say, aluminium hasn't been very formable. We've worked very hard to get its ductility and its elongation better. And by doing that, what it's meant is we can combine what would have been traditionally 2 or 3 parts into one large pressing. So this is the side frame of the Range Rover in the top right-hand corner. And by eliminating all those small panels and all those additional joints, what we get a further weight saving, in this case for this vehicle, of about 3 kilograms per vehicle by using this more formable alloy. We also looked at the total processes that we were using, because we were using a lot of heat-treated alloys. The material itself was being heat-treated at the start of the process in the coil form, and we decided to look at and turn it on its head and say, maybe we could form the parts first and then heat treat them, and look at the total energy we put in to make each individual part versus the total energy we put in to make the coil in the first place. And for certain parts, this is a very good process. If it's a relatively high yield part in terms of its utilization, actually heat treating the parts, if we can get a lot of them in the furnace for a very short time, is actually a better CO2 value than if we heat treat the whole coil, then stamp the parts, then have the utilization of less than 80%. What we find is we're actually wasting, if you like, heat in heating metal that we're not using. So that's another interesting dimension. And again, that gives us about a 52% weight save over the equivalent steel parts. We also use, which we can't do in steel cars, we use what we call high pressure die castings. And we use these because, unlike stamp parts where you've basically got a homogeneous wrought system where it's got a constant thickness, with a cast part obviously we can vary the gauge and the strength of the part by adding ribs and adding form and feature into it over the part. But we developed a special die casting which has got a much higher elongation than the traditional die casting. In that way we can rivet the casting into the rest of the structure. So it thinks it's a bit of sheet, but actually it's variable thickness sheet. So we've got elongation as high as 20% in our castings, which also mean they bend in crash, which is quite useful. We've developed a number of other things, so we use high strength aluminium alloy profiles for things like the front bumper beams and the crush cans, the jacking points on the car, where we can get away with near net shapes without doing a lot of work to them afterwards. We will use standard profiles, so things like roof bows and various other things that are relatively simple shapes. Again, very good material utilization, so not a lot of scrap, and very good from a carbon point of view. So one of the themes in this presentation is all about prototypes. So I thought I'd better put something in about prototypes. Traditionally, we've taken our cars all over the world, tested them from day one, seen if anything breaks, fix that, put them back on test. We don't do that anymore. Everything is done pretty much in the virtual world. So there's about 1.5 million hours of CAE work went into the new Range Rover. So that's about 1,000 years of computing time, just to put it in the context. Now, in doing it on the in the computer environment, in the virtual environment, that saved us about 750,000 miles of testing in the real world, which again, when we add that up in terms of fuel costs and manufacturing costs, saved about 320 tons of CO2 just by not testing as many vehicles. And the other thing that we've started to do, rather than driving vehicles all over the world, we now have what we call simulation rig tests, where we'll have environmental chambers that'll give us minus 40, plus 50 degrees without leaving the factory. So we'll have climate chambers, we'll have climatic wind tunnels, and we'll have rig tests that will simulate durability and corrosion rather than sending the vehicles into the real world. But we still have to test in the real world, but this gives you an idea of the fidelity, if you like, of our CAE models relative to the real car. So this is obviously the CAE prototype, including the occupants and the airbags. This is the real car overlaid with the load paths from the CAE, and they're almost identical. So we build into CAE models things like metal thinning. We build in all of the age hardening, the strain hardening of the parts, what we call the fracture damage. When we're making the parts, we build all that into the CAE models before we put it through a virtual crash or a virtual durability cycle. Same for durability. Our focus is on saving as much weight as possible, so we want to optimize every single part. So we put them through a virtual durability. This is the front shock tower, for example, taking the off-road load case. So we'll look at the thickness across that. This is the jacking loading. So we'll look at how many fixings we need. You'll notice that the thickness of the jacking bracket varies depending on the load that it sees, so we can optimize the wall thickness of a part or where we put the metal depending on the load case that it sees. So we want to get as many load cases into our virtual models as possible. This is just a simple torsion test and then another simple bending test, and you can see the various suspension mounting points lighting up. It's also very good for getting into the detail performance of the individual areas. So we can do things like suspension mounting points, look at the different loading cases. So this is the rear casting on the rear end and the rear cross member. We can do things like what we call ditch recovery. So if someone unfortunately puts either their Range Rover or another car in a ditch and it has to be towed out of the ditch, so it's effectively a dead load, we can simulate all of that sort of load case on the front structure. Same with the rear towing eye. This car can tow up to about 3.5 tons in normal duty. I probably shouldn't tell you the real name. We call this the Fat Man test. So this is just a grab handle bracket, and we put a 200 kilo load through the grab handle to make sure that if someone of more heavier stature does pull on it and literally has their full weight on it, it's not going to give way. But again, more practical towing. We can tow a dead weight of 3.5 tons off the rear end of the car, and again simulate all that in the virtual world before we build any of our prototypes. So that's kind of durability. We do the same thing for what we call NVH, noise, vibration and harshness. Our goal again is to get the lightest weight, so we look at how heavy every single element of the car is, compare it to the previous model. So this is the roof panel, for example. The old roof panel weighed 29 kilos, the new one weighs 17 kilos. We do this for every single panel on the car to make sure that we meet a global performance for stiffness, both in bending and torsion, but also what we call a modal performance, where we're looking at the total vehicle inputs for powertrain, chassis, and any other input to the vehicle, and making sure that all of that, first of all, is aligned on a modal alignment chart, and then secondly, that we can minimize the weight in every single area. So this is the rear end again, looking at the load paths. We go for a straight load path as possible. You know, it's a bit like designing a building. You know, you need to make sure all the loadings are as well distributed as possible, but also that they've got the cleanest load paths that take those loadings. So again, this is the rear suspension mounting points. The advantage of using things like the castings is, as I said earlier, what we can do is we can actually vary the wall thickness to suit the loading that's going into them, and then distribute it as quickly as possible into the rest of the structure. And I enjoy designing castings probably more than I enjoy designing sheet, because I can put a bit of, if you like, artistry into them. So that if you look at the ribbing and all the patterns inside it, clearly these are all done through optimization of the stresses that go into them. But what you end up with is a very elegant looking solution that is, rather than just being homogeneous, you can actually put the material where you need to put it. Of course, it's not just all about materials and parts. We have to look at the joining technology that we use in the car. Again, we decided when we were looking at the aluminium vehicles that we wanted an environmentally friendly joining solution as well as making a lightweight material. So we went for what we call cold joining. In the same way predominantly the car is cold formed, we decided that cold joining was a more environmentally friendly system. So it's basically riveted and bonded together. Now the rivets aren't what you would associate as traditional rivets, where you have to drill a hole and then insert a rivet by hand, and probably takes 10-15 seconds to do. We've actually got what we call self-piercing rivets. These are very, very strong, and when we combine them with the adhesive, we get over 3 times the peak strength and over 5 times the durability strength out of a self-pierced rivet than we would do out of a resistant spot weld. We also need less of them, so if we had about 5,000 to 6,000 spot welds on a steel car, we only need about 3,000 rivets, 3,000 to 4,000 rivets on an aluminium car. And we can do two metal thicknesses and 3 metal thicknesses. Just to explain how the riveting process works, because it is self-piercing, this is just a little diagram. The green part is the rivet itself. The punch pushes the rivet through the top sheet. It engages in the die and splays the bottom sheet to trap the 2 parts together, giving it's almost like a human tooth interlock. It gives a very, very strong joint, very strong mechanical joint, but it also, we've developed the technology now where we can rivet as fast as we can spot weld. Because we're using less of them, we actually have a lower cycle time now on our aluminium vehicles than we do on our steel vehicles. But the advantage of the riveting is it does 3 things. First of all, there is no hot joining in the factory, so we don't need any cooling water. So that's number 1. We have no wastewater in the factory. Before, clearly we were using litres of the stuff to keep the spot welding guns clean and cool. We don't have any fumes from the welding, so we don't need any air extraction. So actually, when you go into an aluminium body shop, it's a little bit clinical and a little bit quiet and a little bit sterile. It's not like one of these things where you've got flames flying about the place. But the third advantage is it uses 30% less energy than a spot welding gun to make a rivet. So although quite high insertion forces, they are not using any transformers, so relatively low electricity take. And we have a monitoring system on each robot that monitors the total electricity used and converts that into CO2 just to see what the advantages are in the factory. So this is just over time. This is the first car we started back in year 2000. The hours per car, i.e. how long it takes to make the body relative to the 2 steel cars, equivalent steel cars over on the right hand side, was almost, well, it was over double its equivalent car. Since that journey that we've taken on, our latest Range Rover launch is now less than its equivalent steel SUV, and we're approaching what we would call the best-in-class steel spot welded saloon car. And we have a plan for our next aluminium vehicle, which we can't talk about, to actually be less than the best-in-class steel in terms of the hours per car it takes to manufacture the vehicle. And I guess the final leg on my stool, if you like, of sustainability is the material that we use. We collect every single bit of scrap that we generate in the process, both at the rolling mills where they make the material and at our stamping plants and during any waste in the system. That means that we use up to 50% of the metal in our car is made from recycled aluminium. Our goal by 2020 is to get that to 75%, which means we've got to start using old cars, basically, end-of-life cars, and what we call post-consumer waste. So my plea to you all would be, stop throwing cans in the bin, stop throwing toothpaste cartons in the bin, and stop throwing packaging, foil, dinner trays, whatever it is, in the bin. Chuck it in this separate bin for aluminium and give it me so I can make cars. It's much better for the environment, it lowers my costs, and it saves you money in the long term, trust me. So obviously most people know that recycled aluminium only uses about 5% of the energy of primary aluminium. We just want to continue to use recycled metal rather than primary. We'll never get to the state where we can use 100% recycled metal, otherwise we wouldn't make any more cars. But we think that 75% is a good number based on the amount of aluminium that's in the value chain at the moment. So we've actually got a project with the British government where we're taking landfill waste and extracting the metals out of that landfill waste, and basically through chemical processes extracting the aluminium and the other materials that go into our cars. So for example, pop bottles, which we haven't got any unfortunately, those PEP pop bottles that we throw in the bin again, it takes 26 of those to make a Range Rover rear quarter trim. So the substrate that we use uses old pop bottles basically. So and again, it's another good use of things that we generally throw away becoming value add and going into premium products. So we think future luxury will be something called sustainable luxury. So in summary, basically we want to use as much recycled material as possible. Up to 95% of the materials in the new Range Rover are fully recyclable, so that we've got a real focus on that. 31.5 kilograms of the plastics that go into the Range Rover are made 100% from recycled plastics. As I said before, 40% weight save on the body, which has meant that combined that with the powertrain downsizing, we've saved over 420 kilos. We have a Range Rover diesel at less than 200 grams, and this year we'll bring a hybrid Range Rover diesel at 169 grams. That's about equivalent to a Mondeo. So a full-size Range Rover with every single bit of luxury and every single off-road capability you want for the same CO2 as a Mondeo. And that's kind of it, other than the last message, which we do internally, what we call life cycle analysis. What we do now is, rather than measuring the tailpipe of the vehicle, we measure the complete life cycle of the vehicle. Our goal is basically to save 10 tons for every vehicle we produce in terms of reducing that versus its outgoing vehicle. So over the life of the car, reduce the overall CO2 by 10 tons per vehicle over its life. Range Rover does that, and at 75% recycled metal, that will actually increase to nearly 12 tons. And we get that certified by the VCA, the British Government Audit Authority. So I think in summary, our goal is to make big cars as light as small cars, downsize our powertrain to reduce our overall CO2 tailpipe emissions, because we have to do that for legislation, but take into consideration the CO2 we generate in the factory and the amount of primary product we're using in the manufacture of the car, with a focus on using as much recycled material as possible. So with that, one thing that we have to bear in mind while we're doing all this, we still have to make cars that people want. We can never make cars that are just very CO2 friendly or very sustainable. They have to have a business case, they have to make sense, and our customers have to want them. So they've got to be attractive to the people that go out and buy them. On that, another video to finish.
Working in Jaguar Land Rover, we've got fantastic resources, fantastic engineering capabilities across our business. At the critical stage of this project, we had a third of all engineers in Jaguar Land Rover working on this brand new car, brand new platform. And being able to harness the skills and knowledge from keep people and bring those things together really means we can move the Range Rover to be the pinnacle of refined capability. Jaguar Land Rover's aluminium manufacturing technology has enabled us to take 420 kilograms out of this car. So when we look at an existing Range Rover, a V8 diesel with an 8-speed that we launched at 11 model year, we have taken 420 kilograms out of that vehicle. We have downsized the engine from a V8 diesel to a V6 diesel with an 8-speed gearbox, and we've maintained the performance. So the 0 to 60 of this time is 7.9 seconds, and the 322 V8 diesel is 7.8 seconds. But the CO2 has gone from 253 grams per kilometre down to 196 grams per kilometre.
One of the principal reasons we use aluminium is for lightweight. The intention is to save as much weight as possible on the body so we can get the secondary weight saves in the vehicle, and that adds to a big change in the performance of the vehicle, not only in the attributes such as ride and handling and dynamics, but also improves the fuel economy and, as importantly now, the CO2. There are a lot of urban myths about aluminium. However, the reality is aluminium absorbs more energy per kilogram than steel. So if you make something out of aluminium, not only do you make it light, but you actually make it strong. This car is very, very safe. The new roof crush test that's required in the US, which is 3 times gross vehicle weight, this car meets and exceeds by a significant amount that test. So aluminium is a good material of choice, not only for lightweight, but for great strength as well. It cuts out in a minute, so I'm going to just move on. Thank you very much.